Okay. We are ready for our next one? Yeah. Okay. I'm really excited to introduce Orri from Meta. Orri is one of the co-creators of Velox and is going to be talking about TorchWave today. So Orri, I will hand you the mic.
Yeah, hi everybody. So I'm Orri from Meta, from Velox, and we'll be talking about how Velox is going towards new frontiers. Everybody's going to AI, and AI is the place to be, universally agreed, so that's where we too are headed, especially in light of the fact that AI is by now indisputably the main consumer of data. So we'll be covering a whole range of topics here, starting from the business case of why we do actually experience an organic need to move compute over to GPU. Then we'll be talking about this pre-proc pipeline and what it is and what are the opportunities and why PyTorch in its present form is not doing that very well on GPU and how we can improve that situation. Then we'll be talking a little bit of tech about how GPUs work and how you can get value from that type of platform, as it's by now like the main compute platform, so we should understand it better. And then we take some examples of kernel fusion, some examples of the actual workload, and then we'll have some thoughts concerning the difference between the AI world and the data management world. After all, you know, they're both talking about arrays, but there's all kinds of subtle differences of semantics. And if we have this mission of unifying compute across all the branches that matter, then our understanding of these spaces and how to unify them is of course crucial to our mission. So like said, AI is the main consumer of data, and Velox has had this objective of unifying compute, being like Dave Cohen said at the very beginning, that Velox should become the ABI for compute. And we are seeing this vision being realized now most recently through the integration with libcuDF, where Velox in fact is the ABI for heterogeneous compute. And we'll be extending the same notion to new frontiers, also including then the training pre-proc and things like that, AI adjacent. The message also already from last year is that the gains from brute force optimization of, let's say, vectorization on CPU or straightforward offload to GPU have been achieved. There's very little low-hanging fruit to pick there. That lunch has been eaten. So now to go further in our mission, we have to understand the application. We have to understand what we are doing, why we're doing. We have to have the big picture. The first instance of this is the introduction of query optimization last year at the same conference. Now, as you heard yesterday, query optimization is well underway. So we're taking charge of the front end, so we know what is the plan to execute and why we're executing it and what are the underlying possibilities in optimizing that. Similarly, this year, we're introducing the full program optimization for pre-processing data flows for training, which is not exactly query optimization, but it is also a language technology about compilation, about understanding the underlying performance potential of the whole application. So now if we look at the data center situation, our biggest application in machine learning is arguably ads. And ads has this odd compute shape where you have a bunch of small servers running DPP that Elodie was describing yesterday. And this DPP runs on these small servers, and then there's bigger servers, typically with 8 GPUs. And then there's always the eternal question of what's the proper mixing ratio, how many front end, how many GPUs. So it used to be 4 T1s for one A100, and it would be 11 of them for a B200. And of course, how many you need on either side will depend on the application, and its mixing ratio is never right. You're always underutilizing one side or the other. So making resources fungible is a big thing, especially now that we're seeing public clouds building things for LLM use cases, which are predominantly GPU. We are building data centers for LLMs, and they are predominantly GPU. And this 40-60 mix of CPU and GPU in terms of power consumption is a bespoke mix that's nobody's building. So if we want to be fungible in where we're running, we need to be consolidating compute on GPU. So this is like the first business case that's really driving demand for compute migration to GPU outside of the core areas of training that have like always been on GPU. So then, let's see. Okay, now are we like wasting these valuable GPU resources by running pre-proc? We are not, because the utilization when we're running training is actually not that high. It's not like half the cycles are taken or something like that. And also there's natural breaks because there are patterns of all reduce and all broadcast, and there's other communication patterns that create like time windows where the cores are sitting idle and the network is busy. So we can interleave pre-processing and training. Now, for the product evolution, last year I was talking about Velox Wave, which is our go at doing kernel fusion and compilation for addressing SQL on GPUs. So we did do table scan with filter push down, and we did group by and hash join and the basic operations like that. But we did not have an immediate road to market for that, because after all, for us to deploy a system for generic data management, we would have to have a GPU data center for that, and the GPU data centers that we do have are geared towards training, and the economics of running data management on that kind of scarce resource just don't work out. So what does work out, however, this year is moving the pre-proc there, because we already have the GPUs. We take the immediately GPU adjacent part of this value chain of training data, which is the PyTorch pre-proc. And then if we can make that essentially for free by merging it in the idle spaces of training, then we already have the platform. We have a huge win, because Python pre-proc or PyTorch pre-proc represents about half the CPU consumption of DPP. Then we would, if we are successful with this, we would be at a ratio of 20 CPU to 80 GPU, which is getting closer, but it's not quite there yet. So, okay, so the pre-proc pipeline in general, it begins with SQL data frames. So like Elodie was explaining yesterday, so this is table scan, reading, filtering, data selection, data cooking for a particular model. So why is there a SQL thing to begin with? It's there because if we did have a materialized input for every model we're training, we would be running out of space. So we need to have like one master table of training data, and depending on what model we're training, we'll be picking different parts of that, different features, different rows. So we'll be selecting from that table, and therefore we'll be running on-the-go transformation first in SQL. And then because training wants to have even-sized batches, we have to rebatch them. So we make random-sized batches because of filtering, and then we make even-sized batches by consolidating them. Then we do tensor conversion. We go to PyTorch, and we run PyTorch programs to massage the tensors, and then we ship that off to the GPU server. And now then the PyTorch part here takes about half the time. And to be on a purely GPU environment, this is a logical first step to moving the PyTorch pre-proc over to GPU. Now you could ask yourself, why isn't PyTorch already like a GPU native environment? Well, for training it is. For pre-proc it doesn't quite work out that way, because we lose a lot of performance by having too many kernel launches and too small inputs. And why that doesn't work on GPU is what I'll explain later. So typically these pre-proc pipelines do similar operations on different features: hashing, bucketizing, some filtering, clamping things to a value range, and so forth. But the typical input size is, if the whole input batch is 1 gig, the individual arrays on which we operate are maybe 1,000 to 10,000 to maybe 100,000 elements. And if your GPU kernel is running on 100,000 elements, it's not running efficiently. For a single kernel launch, you need to process a pretty massive amount of data, much in excess of that. But however, if we have 100 independent operations, each with 100,000 inputs, then the situation is already much better, and we can create what we call a full wave. That's a GPU term for a single request that will saturate the device. Okay, So the way TorchWave works is plugging into the PyTorch execution framework, where PyTorch first runs everything in Python interpreted mode, and then it produces a trace, which is called an FX graph. And this graph is like a trace of the compute that took place. And then any kind of compilation engine will then have this graph and a sample input as its input, and then it will compile it to whatever target. So Torch Inductor compiles to Triton, TorchWave compiles to CUDA kernels with a runtime compilation, and there's other runtimes that do other things. But there is a generic means of plugging in these things. So in specific, what TorchWave does when it sees a graph, it will eliminate, do some simple transformations, eliminate no-ops from there. But the interesting part begins with like detecting multiply used computation. So if something is used many times, it should be completed before its first user begins. So then we cut the graph into layers. So suppose we have 500 independent operations. So then we look at all of these and see what are the inputs that are accessed by more than one. And then we put all these inputs that are multiply used in a separate layer. And then we look at that layer, are they multiply used things, and then we put them in another layer. And so then we execute these layers in sequence. But once we have layered these things, we have these layers that have hundreds of expressions each, and these expressions are guaranteed within each layer to be mutually independent, so you can execute them in parallel all at the same time or in any order. And then, having done this, we can look at this compute and then figure out how to make CUDA kernels from these by fusing them. And CUDA kernels GPU is an interesting platform because for any one algorithm that you want to execute on there, you have like a ton of different implementations, which will be, you will have to pick between these implementations based on your input size and based on other environment criteria. So it's a particular kind of puzzle. But the bottom line is that what is logically serially expressed but logically independent becomes explicitly parallel. So when programming GPUs, the basic unit of programming is a thread block. So that's a bunch of threads, like the name indicates, that are running the same program. So typically 256 threads per block. And then a grid is when you have many blocks. And a kernel launch is something that starts a grid on the GPU. And this starting a grid on the GPU does not come for free. It has, even if it doesn't do anything, it takes about 10 plus microseconds to start it and then see that it has finished. And then each of the blocks in the grid, setting up a new block is not for free. It's a microsecond or two. And therefore, these blocks should run for some double-digit number of microseconds at least. And the grid is not very efficient if it's running for less than 100 or 200 microseconds. Milliseconds are better. So then, given these constraints, there's a few types of things that are done on GPU. So element-wise is simplest. It looks just like a loop over an array. So you combine the first element with the first element of one, with the first element of the other, and you produce a result. And that's very straightforward. You can run that as wide as you want. And of course, as long as every block has enough work, it's a good fit for the platform. So matrix multiplication is not exactly element-wise, but it too is something that can be scheduled into pretty much infinitely many independent operations, and all you need at the end is one barrier to see that everybody's finished before you access the result. So then the other kind of operation that we run on GPUs is reduction of different sorts. So anything that is adding up elements of an array or filtering sets or doing prefix sums or anything like that is a reduction. And these can be implemented based on input size in a few different ways. So if you have a single block, then it's pretty simple. You just add up 256 elements in a highly parallel fashion, and then you remember the sum, and then you do the 256 next, and you remember the sum, and you do 256 next, and so on, which is very efficient, but it's not very scalable because you're hitting a tiny fraction of the device throughput. However, if you can do this algorithm on 100 or 200 inputs at the same time that are independent, it works very well. But if you have few big inputs, then what you got to do is do this in multiple stages. So you split the array into independent parts, you add them up, add up the sum on first and second and next, and then you add up these sums in a separate kernel launch, because you have the first sums have to be computed before you can start with the second one. And then finally you end up with 3 kernel launches. And then you can hit more throughput, but the efficiency is something like 4 times worse. So then there's an intermediate form to just, you still need barriers, but you can have, normally you have a barrier between kernel launches. So you launch a kernel on one stream, it finishes before the next kernel that you launch on that stream begins. So that's a barrier. You can also do a barrier while staying on device called cooperative grids. That has less latency, but it can tie up resources if the utilization is not even across all these blocks. So there's many different ways of orchestrating this compute. Now we look at the use case here, keeping this in mind, because we'll be deciding what to do based on input sizes, and all of these implementations of one algorithm have their place here in this architecture. So here is an example. So what it does, this expression, what it does is not on the face of it readily obvious, but we can look at its components, and we see one reduction, which is a cumulative sum, a prefix sum. So every array element is a sum of all the elements before that. And then we have a bunch of element-wise operations like subtraction and clamp to, clamp a value to between bounds. And then we have a bunch of views, like that's extract without copying slices of tensors. And concatenation is also a view operation, because then the inputs can fill in different slices of one big tensor without intermediate materialization. Okay. So then expressions like that in this one graph, we have a few hundred of them. So you can imagine like figuring out with the graph by looking at it is not readily obvious. But when we analyze it, we see that it falls into 13 layers. And many of these layers are some of them are compact, but many of them are tens of operations wide or hundreds of operations wide, which means that there's latent parallelism to do what normally would go sequentially about 100 operations at a time. And so this is this is the core knowledge, the core insight that we start from. So now, knowing that we have so much independent work to schedule, we have to translate this into kernel launches. And what the default operation does is doing them one kernel at a time, which hits this 100 or 10 microsecond latency several thousand times, so all you get is latency. But if you merge these operations together and put them side by side in one kernel launch, then your situation is radically better. So what can you fuse? What is fusion, first of all? If you have A plus B, and that's one kernel launch, and then plus C is a different kernel launch, that's not fusion. Fusion would be A plus B plus C in one kernel, and then it means that you have to generate the code of the kernel and compile it on the go to have it ready to execute. And this is the kind of fusion that torch inductor does. We do a bit more fusion because we can combine this with any kind of reduction. Again, if we're running a single block wide per expression, it's very easy because we can just put a sync threads between the input and the next stage and the next stage, and it's easy to synchronize that all the input has finished before you start the processing. You can do that at almost no cost if it's a single block wide. If it's a few blocks or tens of blocks wide, you can do a cooperative grid, and you can still stay on the device, and you can keep putting more and more operations in one kernel launch while running wide and staying on device. So the only thing that is not conveniently fusible is a situation where you first compute the size and you don't know the maximum for the size, and then you have to go back to the host and allocate the memory on device, and then you have to then pick up the computation. But that happens only 3 times in this whole graph. So typically we know the maximum size of the result even because we have reductions, but we don't really have like explosion of cardinality. So this is how we orchestrate that. Of course, fusion has some limitations as well, because GPU likes simplicity. So there's a thing called register pressure. If your program is complicated, it may require many registers to run, and the more registers it requires, the fewer instances of that program fit concurrently in a GPU core called a streaming multiprocessor. So then this is why actually this vectorized interpretation that Velox is doing does not very well fit on a GPU, because if you have a big kernel that has every operation you could conceivably do rolled into it, some of these operations are complex and they take many registers, and then everybody's occupancy suffers. Occupancy means how many of any one particular thing fit at the same time on the device. So then it's kind of smart to put all the simple things together and all the complex things together. And this type of information can guide the fusion decisions. Okay, so torch wave capability, it being a native executor, it does not have to fuse absolutely everything. So the adjacent and consecutive parts that are all understood and supported can be fused pretty much without restriction. But then you can have some things that you leave unfused if they're big enough standalone by themselves. So adopting a thing like that does not require that you have custom implementation for everything, because you have a GPU fallback. And if the GPU fallback is efficient, meaning that it's doing enough work with few enough kernel launches, then you can leave it be as it is. So there's to give an idea of the amount of parallelism, the grid, we have typical thread blocks of 256. You can fit a few hundred of them on an A100, on a B200, you can fit some 50% more of them. It's a reasonable thing to say that to make a full wave, you should have like 600 to 800 blocks of these things. And of course, if you have an integer multiple of that, it's even better, because then you keep the device busier. And oversubscribing on CPU is not always good, but oversubscribing on GPU is most of the time. I mean, I cannot think of an example where it would be harmful. So having a lot of work in flight is the thing. So this GPU programming, you can liken it to the game of Tetris, this first video game of all, where your win is when you get the whole width of the box full of these squares, and then you got these squares of these rectangles of different shapes that are falling from the top of the screen, and you have to rotate them so as to make solid lines that are fully occupied, and that's the analogy of your full wave on the GPU. So GPU, everything is kind of a square, and the GPU is a bigger square, and then you put these small squares packed as best you can within this bigger square. So that's the mental model that I find helpful to describing this. Okay, so then of course you have, when playing Tetris, you have to have good reaction time, because you have only so much time to decide which way you're going to rotate the block that's falling. So this is a scheduling overhead. So in some cases we find that when we can execute in 20 microseconds, it takes us 200 microseconds to decide exactly which should execute how wide. The trick here is, of course, we have many operations going in one kernel, and these each operate on different input sizes. And then depending on the input size, we might decide to do it a single block wide or multiple blocks wide. These operations also have a cost. So if you know that your operation is expensive, you will give it relatively more blocks than a cheap operation, because your other objective is that every block in the launch finishes around the same time. So there's all kinds of scheduling magic that we have to do, but we have to be deciding very fast. Now the good news here is that in these training workloads, all these data sizes are within 20% in one batch to the next batch. So typically you can cache these decisions. Okay, so here is a micro benchmark. So we have a tiny little thing, a PyTorch expression that adds up 2 tensors, and then it picks 9 out of 10 elements of the result based on a modulo of the size. And then we're running this with different input sizes and different numbers of these going concurrently, and we're comparing the 3 kernel thing, where you first do intermediate sums, and then you add up the intermediate sums, and then you finally move the data to their destination, either in 3 steps for a big input or in 1 step for a small input. And what we're seeing is, as long as we have enough small inputs, then the single block tends to win. And then we can see, based on the strictly sequential execution on GPU, we can see crazy multipliers depending on your input shape, like 60x or something like that. So mileage will, of course, depend on the actual application, but the fact of the value of launching a lot of work at the same time is foundational, and that's not in doubt. Okay, so now some thoughts about the kind of, if we come back to our mission, which is to unify compute across these value chains, and ultimately to create a better user experience, because this right now making these AI applications, recommender systems in this case, involves first this managing the data and putting together these training tables, typically big Spark ETL jobs. And then there is this other stage of pre-training, data reading, and data massaging in SQL on one side and PyTorch on the other side. And then there's the model architecture in the training proper. And so if we would have to have, and it's not exclusively Velox's task, but it should be an objective of our organization to have like an end-to-end understanding of this and to see what is a good way of talking about these compute flows. So now we have gotten a bit further into understanding this stuff because we have hands-on experience in both data and now also on tensors. And we have a few observations on what are the differences. Because if you squint, they're kind of both arrays. So, but there's some fundamental assumptions are somewhat different. In SQL, we're streaming through a bunch of rows, and typically we're talking about operations on scalars, and then these operations become operations on vectors by vectorization. But when we are talking PyTorch, we are also always talking about having a full data set materialized and materializing full intermediates, and always doing an operation on whole arrays, whereas SQL has a more like streaming mindset where you batch things that happen to be consecutive, whereas in PyTorch this batch boundary is very explicit and there's really no idea of streaming. There is quite a bit of functionality for multidimensional arrays in PyTorch, whereas we have a lot less of that in the data management side. There is a notion of zero-copy view on both sides, a dictionary encoding on one side or a slice of a vector, and then we have a pretty rich view semantics with all kinds of strides and zero-copy reshapes of tensors in PyTorch. So then this PyTorch model of doing an array operation at a time is really good on GPU because it's already like vectorized, so to say. But if your arrays are too small, it's no good because you need to have, I would say, tens of millions of inputs worth for a single kernel at a time approach to be effective. So this is the gap that TorchWave is filling, that is taking everything that's small and independent and making it into larger waves. Okay, so there's an A11 library that is the other interesting difference, or let's say user experience for these training workflows, is that you have kind of batch semantics on the SQL side, and you have full data set at a time semantics on the PyTorch side. And then when you go from one to the other, you lose some context. So you don't necessarily know, for example, what is the batch dimension. Even though one of these dimensions of these tensors represents the position in the batch, you don't know what dimension it is. So A11 is an addition to the tensor format that seeks to preserve this data and to create more transparency about the semantics. So the semantics carry better from one side of the fence to the other. Okay, so going forward, the basic arithmetic I'd like to leave you with is we have, on a modern GPU, we have host-to-device bandwidth of maybe 50 gigabytes per second, but the device internal bandwidth is over 100 times greater. So if we take the assumption that to pre-process one item of data, you need about 10 memory accesses, we should be done with a pre-proc if we're running at full device utilization in a tenth of the time it takes us to copy the data into the device to begin with. So this is the contention why we say that pre-proc could be for free. Now, of course, if this is all realized and we will be running our first end-to-end pipeline because we have enough feature coverage now. In the next couple of weeks, we will see how that goes. And ultimately, we'll tweak it until we have full device utilization and this bet is realized. Of course, this, when fully successful, is going to give us a mixing ratio of 20/80 between CPU and GPU, and that's not quite where we want to be because our destination would be more like 5/95, which then creates this organic need to also move the data frame, the SQL data frame and the table decoding and all the SQL gear into the GPU as well. And that is something that for which there will be a use case later. And this would be basically the first meta use case where we have a clear business case where it is obviously beneficial and needful to move traditional data management compute into a GPU, and then we shall see about all the libcuDF and Velox Wave and all these different things that could be tried in that space. So that is exciting because our vision of this end-to-end GPU first data center is actually being realized even ahead of our expectations. Okay, so thank you.
Okay, I think we are in a break now, and we will reconvene in about a half an hour. Thank you.